I'll mention that I'm the co-director of something at Carnegie Mellon University in Pittsburgh called the Center for the Neural Basis of Cognition. It's a fairly unique program that cuts across both universities, involves about 150 students and about 60 to 70 faculty. So we have a fairly unique community of people here interested in everything from the low-level cellular dynamics and neural systems all the way up to large-scale brain systems and brain injury and traumatic brain injury, things like that. In the session today, I think you're going to actually hear some interesting things about high-level core structures of the brain all the way down to nanoscale systems. We're going to really do almost what Jeff Clifton was talking about in terms of one of his pictures. We're going to zoom in and out at different points in terms of the talk. I hope you're having a good time in Pittsburgh. For those of you that haven't been here before, and it's always sunny and warm like this, by the way. We just don't tell people. So our first speaker today is a local person, Frank Ye, who's going to be speaking about mapping brain connectivity, diffusion MRI, applications, limitations, and opportunities.
Good morning. So for introduction, here I'm showing a figure called stratigraphy. It's viewing from the left side of a human brain and showing the connection in the left hemisphere. The data from a normal subject taking 1 hour scan in a clinical MRI scanner. And the data are processed by a technique called diffusion MRI fiber tracking. So here's an overview of this technique, so make it more understand. First of all, we acquire diffusion MRI, as shown here, and which is sensitive to microscopic movement of water. And then by modeling the diffusion distribution, we'll be able to tell the local fiber orientation, and then we can connect those fiber orientation to get the fiber track of the whole brain, creating the figure I just shown, the stratigraphy. So if I'm going to review the detail of the modeling method, which is the most important step. There are a lot of ways to model the diffusion patterns. One of the early approaches called diffusion tensor imaging, still quite popular today, is actually modeling the diffusion pattern as a Gaussian distribution. So in fact, essentially it only needs 6 sampling in the diffusion encoding space and then calculate the diffusion tensor and get a fiber orientation. But this model is really limited and not solve the crossing fiber problem. So more complex models have been proposed, like multiple tensor, spherical harmonics, deconvolution. They sample on a sphere in a diffusion encoding space, and then to fit the model, trying to get the fiber orientation. Now finally, a group at NGH proposed a method called diffusion spectral imaging, DSI. Instead of modeling the distribution, they sample the whole space in the diffusion encoding space and then do invert Fourier transform to get the overall diffusion distribution itself. And then the fiber orientation can be determined by the peak orientation of the distribution. However, this technique is in fact a 6-dimension data set, so it requires a lot of sampling. A typical scan can go up to like an hour or even more, and which is limited its application in clinical study. So there's an active research question whether we can reduce the sampling, find out what's the redundancy in the data set, and then try to shorten the scanning time. So I propose a model called mixed diffusion model, which in short says that the overall diffusion distribution is a linear combination of the component distribution, and each of the component corresponds to one fiber population. And this model can be extended to a linear combination of a series of components, and the components are oriented in all directions. So the interesting thing about this model is it turns out that most of the coefficients are 0, whereas the 1 correspond to the fiber orientation are positive. So the coefficients are sparse. And then by using this extension, I'm kind of transforming the fiber orientation problem to a model selection problem, which can be solved in statistic field, machine learning field. So here I'm applying a popular method called lasso to make use of this sparsity feature and then optimize it to get a coefficient. So here's the result. I applied the model to the DSI sample data set. On the right-hand side is the full DSI data. You can see nice fiber crossing, showing corpus callosum, the fiber orientation. It takes 202 direction. On the left-hand side, it only takes 40 direction. That is 20% of the original sampling. And we can see nice fiber crossing, very consistent fiber orientation. And this has a huge benefit for clinical study because like on 1 hour DSI scan, now we can possibly reduce it to 10 minutes to 15 minutes and then still get quite decent fiber orientation. I can also apply it to DTI dataset, which a lot of groups are already acquiring those dataset. Here I'm showing 30 direction of DTI. That's 15% of the sampling compared to full DSI dataset. And we can still see quite nice fiber crossing, consistent fiber orientation. Now, so for a lot of groups, they already get DTI dataset, they can reprocess the data and then maybe get new results from it. Also, the coefficient mentioned from the model can be summed up to give a new index that reveals the fiber volume fraction, which is showing in the lab. On the right-hand side is a popular index called fractional anisotropy, calculated from diffusion tensor. The important things about fractional anisotropy, FA, is that a lot of people are using this index to do fiber tracking to determine where's the termination of fiber. But as shown here, I'm annotating a region called central semiovulate. It's the fiber corpus callosum cross the choroidospinal tract. And the crossing of the fiber creating a decrease in the FA value, and this known in this field, and often cause the fiber tracking to terminate prematurely. But the index I derived from this model is showing a nice, clear separation from the white matter and gray matter, and it can improve fiber tracking and prevent premature termination. So here's an example. Here I'm showing the DTI fiber tracking using a limited model to track the corpus callosum. And we can only show the fiber going to the top, but the anatomy evidence showing that the corpus callosum fiber is actually connecting the cortex from top to bottom. And here's a figure showing, it's also from the same DTI dataset, but processed by the model I proposed. Now we can see nice fanning pattern connecting to the cortex and pretty consistent with the anatomy we found. So I've introduced a method to solve the sampling problem, but the analysis of the stratigraphy is still very challenging because each individual brain is unique and we cannot just compare them directly. So I developed a method called Q-space diffeomorphic reconstruction. It's doing some kind of special transformation for DSI dataset. And as you may remember, I mentioned DSI dataset is a 6-dimension dataset, so it involves the spatial transformation in addition to reorientation of the diffusion distribution. So left-hand side is the subject data, and then transform all the information, 6-dimension information, to a template space. So now I can process all the data, put it into the same common space, and then facilitate further analysis. So using this method, I apply it to a total of 90 subject data is collected from National Taiwan University, and then create the first DSI template, and it's open to the public. And it also gives a lot of information about the normal population of the brain connection. I can also do fiber tracking on this template, and it's showing the representative fiber track. So it's the major trend of the brain connection is showing here. Then it can also be used to like doing structural connectivity study and to study the pathway of fiber tracks, for example. Here's a paper published last month by the neurosurgeons at UPMC. So what they did is do a microdissection, try to define pathways called middle longitudinal fasciculars, and they claim that the pathways stop at the superior temporal drivers, but they can only do limited subject of study. So in this study, I provided a 90 subject template for them to do fiber tracking. So as they do a fiber tracking, as we can see here, they get consistent pathway that match their finding in the microdissection. So this template actually gives them a solid proof to their hypothesis and then their study. Another application is that I can do vessel by vessel comparison between the normal subject group and the patient group. And once all the subjects transform to this a common space, then I can do permutation tests to get the difference mapping, and then process by superficial clustering, FDR control, try to find a region with significant connectivity increase or decrease. So here's a case I applied to study the connection change of a chronic stroke patient. The images are taken 3 months after the onset of stroke. So the active is not the active stage, but the chronic stage. And the brain structure already has been remodeled in some sense. And in the traditional like T2 weighted image, it shows the lesion is at the putamen. It's a hemorrhagic stroke. But that's only what we can see. We cannot see what's the involved fiber pathway. But by comparing this subject data with the 90 normal subject data, I can reveal the region with significant connectivity decrease. And then it shows that the decrease of the fiber pathway involves the whole the anterior branch of the coronary radiata, and it's far more widespreading than the traditional imaging method. So for a short summary, I have mentioned several limitations in diffusion MRI techniques, including the sampling problem, how to do the analysis. I've shown the application, how to reduce the sampling, and also a DSI template that can define and study structural connectivity. Also, I can do vessel-wise comparison to compare patient group and then the normal subject group. There could be a lot of future works, like applying machine learning. Once everything is in the common space, there are a lot of tools that we can just apply it and see if we can do subject classification. Like in the future, we could do automatic classification and just get a short time of scan and possibly define and then diagnose the disease. I would like to acknowledge the lab at NTU providing 90 subject data set and open it to the public. Also Department of Neurological Surgery, UPMC. Thank you. Thank you for your attention.
How sensitive are you to the choice in maximum L1 norm for the lasso problem, and how do you choose that?
So you're mentioning the sampling problem, the model?
Way up front, your lasso problem.
Yes. Let me get to it.
Yeah,
Okay, here.
Yeah, how sensitive are you to your estimate of S? And
Yeah.
how do you choose it?
So A lot of laser study they get select. Actually, a lot of laser study they select all the model, but here I can apply a prior information that is in a single voxel. We can only get like 4 or 5 fiber orientation. So the simple way I can do here using this prior information is once I select like 4 fiber or 5 fiber, then I just terminate the optimization and just improve the computation time here. So the selection is pretty dependent on the prior information you can provide it, and it works pretty well because like the brain connection, we won't have a lot of crossing fiber oriented at all directions, just like 3 or 4 directions here.
So like in this model, how do you validate that 20% sampling is sufficient and then the graphic that you get is a true representation of the real connectivity? And my second question is, in the 90 subject database that's taken from the people in Taiwan, and how applicable that common space to worldwide human species?
Yeah, very good question. The first question is about how to do the validation. Due to time limitation, I didn't put a lot of detail in this presentation, but I did some kind of sensitivity study and specificity like study, try to compare. I have a golden standard that's from the full sampling of the DSI, serving as a gold standard. I can compare the angular deviation and then to validate the method, but I'm not showing here as an example. And then second question about the 90 data set. It's really limited. I can say that the data is so collected in Taiwan, and I agree that it could be a problem if we apply to a wider population. So a better choice would be like collecting data from multiple different centers. And I know there's a lot of projects still going on, like the Human Connectome project. They are collecting a lot of DSI data set, and it's also open to the public. And in the future, we can just apply the method to the data set and summarize all the information together.
Tim, do you have anything to add on that?
Well, I mean, there's a lot of issues at play with looking at normalized DSI data sets because the way you acquire data sets will change some of the distortion parameters that you carry through the space. So, I mean, law of large numbers is always in our favor if we can apply thousands of grains, but I think applying M&I normalization is good for local data sets when you're comparing within your grid ones.
From a validation point of view, isn't there also a group at Pitt that's taking cadaver heads and then having them sliced and doing an actual neural dissection to actually map the fiber tracks and comparing the data?
That's another thing that's kind of been going on for a while. I'm not sure what the state of the project is, but even then, when you're trying to compare against cadaver data, when you extract the brain, the morphology of the tissue changes as well. So things like comparing it against PI, fluorescent imaging, and that kind of thing would be another useful way of doing it. Also, interspecies tests as well. You can scan a pig and keep the slice and take that all in one shape. You can start to do these comparisons. But I think we're still a long